Wanted to work through an example of Einstein's famous equation, E equals mc squared. The equation tells us that mass is a form of energy, just like motion is associated with energy, just like there's energy carried by light and other radiation, just like there's chemical energy in a battery. In this particular question, we're asked to think about a nuclear reactor. And in a nuclear reactor, in a typical nuclear reactor, uranium, which is a very heavy element, is split into smaller elements. And in the case that we're thinking of, uranium is split into barium and krypton. And the process by which it's split into two lighter elements is a chain reaction involving the uranium absorbing a neutron and being split into two lighter nuclei and also emitting neutrons. So the fact that you put neutrons in and get neutrons out allows you to create a chain reaction, allows you to create the fuel in a nuclear reactor that is turned into thermal energy. Heat energy is turned into electrical energy that we consume. Now, this nuclear reaction is similar to a chemical reaction. So in this nuclear reaction, the mass of the products of the reaction is actually less than, a little bit less than, the mass of the parents of the reaction. And the difference in mass, the loss of mass, corresponds to a loss of that form of energy. Mass is a form of energy, and corresponds to that amount of energy being released as thermal energy, as kinetic energy, because energy overall is conserved. So it's through this reaction that we turn mass into thermal energy, kinetic energy. It's just like the reaction when you strike a match. When you strike a match, the tip of the match has a coating of sulfur, phosphorus, and when you strike the match, you're igniting a chemical reaction that turns the sulfur and potassium into sulfur oxides and potassium oxides. The mass of the products, the sulfur potassium oxides, is actually a little bit smaller, a really, really, really tiny bit smaller than the mass of the original sulfur and potassium and oxygen that reacted. And so that little loss of mass, which is a form of energy, becomes a gain of kinetic energy, thermal energy. And the same thing happens on a grander scale, a larger scale, in a nuclear reactor. So in this question, we've got this reaction of a neutron being absorbed by uranium. It's an isotope of uranium, uranium-235. It causes the uranium to fission, we say, to break into these two sort of splinters. This isotope of mass 141 barium, this isotope of krypton 92, and several more neutrons. 3 neutrons are emitted. And as I say, if we add up the masses of the daughter nuclei over here on the right, and we add up the masses of the parent nuclei over here on the left, we find that the mass of the products is less than the mass of the reactants, and that energy is released as kinetic energy. It goes to make the thermal energy in a nuclear reactor. So let's calculate that kinetic energy that's released. To do that calculation, we've got to subtract from the energy that's equivalent to the mass of the uranium, the energies that are equivalent, and the neutron, the energies that are equivalent to this barium krypton nuclei and these 3 neutrons over here. So I'm going to write that out, and then I'll say a few words about it. So here's the equation, and it's got over here on the left-hand side the kinetic energy that is released. It uses Einstein's famous equation that the energy equivalent of a mass is mc squared, and it applies that equation to the parent nucleus, in this case, which is uranium. So this MuC squared is the energy equivalent to the mass of uranium. To the daughter nuclei, the barium and the krypton, so there's a MBA C squared for the barium's energy that's equivalent to its mass, and an M subscript Kr for C squared for the energy equivalent of the krypton nucleus mass. There's another little term over here. To undergo this reaction, it's a chain reaction. You put neutrons in, you get neutrons out. Putting 1 neutron in, we're getting 3 neutrons out. And so in this equation over here on the far right, I'm accounting for the fact that I put into the reaction, into the reactants, 1 neutron. That's the one here. I release in the reaction, out of the reaction comes 3 neutrons. And so I have this additional piece over here. Be careful with the way I wrote the minus signs. So to calculate the kinetic energy released, we've just got to calculate all these terms that are sitting over here on the right-hand side, which means looking up the masses in a table of all these nuclei and the neutron, and multiplying these terms by c squared. So I've done that. Now, in the table that I looked up the terms, the masses, the units were atomic units of mass. 1 atomic unit, we would write it as U, that unit, is actually equal to 931 MeV over c squared. The units MeV over c squared that we've been using for subatomic particles. So when I solve this problem, I'm first going to work out this kinetic energy in with these atomic units, because my table that I look the masses up used atomic units. But then I'm going to convert it into MeV to see the number of MeV released in one of these chain reactions, one of these chain nuclear reactions. So let's start filling in the numbers. I'm going to pull out a common factor of c squared that you can see here. So that's one thing I'm going to do when I write down all the quantities, and I'll write the units U also as a common factor. So I'm just going to fill in the masses as the numerical values of U. So for the uranium, I looked it up and it's 235.044. For the barium, I looked that up, it's 140.903. For the krypton, it's, again, I looked it up, 91.907. I have to be careful with lots of digits here. And then for the neutron, I also looked that up. Now, 3 minus 1 is going to be a 2. I'm subtracting off the equivalent of the 2 extra neutrons that I produced. So this is going to be 2 times 1.009. That's the mass of a neutron in atomic mass units. All these numbers have units of U, and are going to be multiplied by c squared. So I carried out the addition and the subtractions in this equation. And one thing you discover is that these numbers, these masses, almost cancel out, but they don't quite cancel out. What you discovered is that the mass of the parents, so that's the left-hand side of this nuclear reaction, is a little bit bigger than the mass of the daughter nuclei, the right-hand side of this reaction, by 0.215 atomic mass units. And if we want to calculate the energy, and that's c squared times this amount of atomic mass units. And if I want to convert this number to MeV, then I would multiply by the conversion factor with that 1U, one atomic mass unit, is 931 MeV over c squared. And so if I carry out this little calculation, I mean, the number is 0.215 times 931, so that comes out to be 201. And the units are going to be, well, we've got a U in the numerator here and a U downstairs in the denominator here. We've got a c squared in the numerator and a c squared in the denominator here, just left with the units of MeV, which is a unit of energy, mega electron volts. So that's the amount of energy, about 200 MeV, which released by one of these nuclear reactions that's happening inside a nuclear reactor. Just as a scale comparison, when we strike the match and we have a chemical reaction in which we take the phosphorus or the sulfur and we oxidize it with the oxygen in the atmosphere, in one of those chemical reactions, the scale of the energy that's released is a fraction of an electron volt. This energy that's released is 200 million electron volts. So this single nuclear reaction is releasing millions of billions, literally billions of times more energy than one single chemical reaction. That's the power of nuclear reactions.